Hello, everyone, and welcome to this lecture. In today's lecture, we will be covering network programming. This is the outline of the lecture. We will first start with some fundamentals on networking, and then we will discuss about how kernel sockets and particularly how they work, what their API is, and many other things. We will also list some tools for monitoring the network traffic, as well as other approaches for networking. Traditionally, different nodes on machines communicate with each other in a client-server architecture, as shown in this picture. The server is usually one or more long-running processes that owns and manages some resources. The server process accepts, receives, and processes clients' requests. On the other hand, clients send requests to the server over the network and probably wait for some reply. The communication is achieved through the transport layer, namely the network medium, which transfers the data between the two endpoints of communication. The communication between different nodes is achieved through the networking protocols. A networking protocol is a set of rules that describes how the information is to be transmitted across the network. Networking protocols are generally organized as a series of layers. Each layer builds on the layers below and adds features that are made available to higher layers. This technique is called encapsulation and offers transparency because each layer shields higher layers from the operation and complexity of lower layers. With encapsulation, an application does not need to know the internal details about the protocol. For example, how TCP implements reliability. Applications need to only pass the data down, and sockets are the mechanism to do so. As shown in the figure, the TCP/IP protocol is a layered protocol. It includes the Internet Protocol layer, called IP, and various other protocols above it. The lowest layer is the data link layer and consists of the device driver and the hardware interface, that is the network card, to the underlying physical medium. The data link layer transfers data in the form of frames across a physical link in a network. Frames can be at most as big as the maximum transmission unit, or the MTU. Note that different data link layers have different MTUs. Above the data link layer is the network layer that delivers packets from the source host to the destination host. Each packet is sent independently, possibly taking a different route. This layer performs a variety of tasks. For example, it might break the packets into smaller fragments to help transmission through the data link layer if necessary. Also, it is responsible for routing data across the internet and providing services to the transport layer. In the TCP/IP protocol suite, the principal network layer is IP. IP is connectionless and unreliable. It makes the best effort to transmit datagrams from the sender to the receiver, but doesn't guarantee that packets will arrive in the order they were transmitted, that they won't be duplicated, or even that they will arrive at all. Nor does IP provide error recovery, and reliability must be provided either by using a reliable transport layer protocol like TCP or within the application layer itself. IP may fragment datagrams. When an IP datagram is larger than the MTU size, IP fragments the datagram into suitably sized packets for transmission across the network. These fragments are then reassembled at the final destination to recreate the original datagram. Above the network layer is the transport layer. There are two widely used transport layer protocols in the TCP/IP suite. Firstly, the transmission control protocol, or the TCP, is a protocol used for streaming sockets, whereas the user datagram protocol is a protocol used for datagram sockets. Streaming sockets provide us with a reliable and bidirectional communication channel. In contrast, datagram sockets do not implement reliability. The messages might be lost, reordered, or duplicated. Additionally, the receiver might drop packets, and that could happen if the queue or buffers are full. There is also a raw socket type called sock raw, which allows an application to communicate directly with the IP layer. We don't describe the use of raw sockets since most applications employ sockets over one of the transport layer protocols like TCP or UDP. This is a table with the most important sockets API. A call to the socket API creates a communication endpoint, whereas bind attaches an address to a socket. Listen and accept are usually used by server applications to listen to incoming client connection requests and accept them. The connect call is used by clients to connect to remote servers. And to exchange data over the previously established connections, applications rely on either the send and receive call or the read and write call. And finally, the close call releases the connection after the usage. To the kernel, a socket is an endpoint of communication, whereas to the application, a socket is a file descriptor that lets applications read from or write to the network. Clients and servers communicate with each other by reading from and writing to socket descriptors. The main distinction between regular file I/O and socket I/O is how the applications open the socket descriptors. These are two diagrams of how a client-server model works for stream and datagram sockets. A typical stream socket server creates its socket using socket calls and then binds the socket to a well-known address using bind. The server then calls listen to allow connections to be received in the socket. Each client connection is then accepted on the listening socket using accept. A typical stream socket client creates a socket using socket call and then establishes a connection by calling connect, specifying the server's well-known address. After two stream sockets are connected, data can be transferred in either direction using read and write. With the close call, the connection is then terminated. A typical datagram socket server creates a socket using socket and then binds it to a well-known address using bind. Datagram sockets are connectionless. The server socket can be used to receive datagrams from any client. Datagrams can be received using receive from system call, which also returns the address of the sending socket. A datagram socket client creates a socket using socket and then uses a send to send a datagram to the specified server's address. By default, the sys-calls we saw are blocking. For example, a receive system call will block if there is no data to be read. However, the blocking API is restrictive in the presence of multiple clients. This is because blocking calls are not sufficient in the presence of multiple connections, where an application may have to simultaneously send and receive data while also doing some other work locally. To overcome these limitations and to be able to design servers that scale better, these syscalls also come with a non-blocking version. We first need to set the socket to non-blocking mode. Then after doing so, all the operations will return immediately. As we will show later, the application requires to poll the sockets to see if any I/O operation is available. Furthermore, the kernel and modern languages also provide us with asynchronous I/O. In that case, the application submits the request or syscall and gets notified from the operating system when it is completed. Now let's discuss the server's design. Firstly, when we talk about the server's design, there are three major types. The first kind of design is an iterative server design. This is the most intuitive design, wherein a server handles one client and one communication, or rather one connection at a time. Additional clients can connect while one is being served. So the connections are established and clients are able to send requests, but a server will respond after it finishes with the first client. This works well if each client requires a small bounded amount of work done by the server. Otherwise, the clients will experience very, very long delays. The next kind of server is known as the multitasking server, and this is to usually support processing multiple requests in parallel. So in this case, a multitasking server would create multiple processes or threads that can handle one connection or one client. This design offers the parallelism, but incurs very high overheads due to threads and process creation, and also due to context switches and scheduling. Lastly, its scalability is very, very low. And finally, to overcome all the limitations and improve the scalability, a server could multiplex the communication channels through a multiplexed I/O design. More precisely, each thread or process can handle more than one connection, and to achieve this, non-blocking sockets are required. So in this case, each thread or process, which is assigned a set of connections, polls or periodically checks whether any of the active connections are able to perform any I/O. For example, if there is data to be read. A similar design could also be used, or rather could be implemented using asynchronous I/O via the select and poll system calls. To monitor non-blocking sockets, we have the select, poll, and epoll at our disposal. All the three syscall monitors include a set of file descriptors, and they poll these file descriptors to see if any I/O is possible. So the select API is faster for a relatively small number of connections, about 1,000 sockets, whereas the poll API scales better with more open sockets. ePoll is similar, but it can be used as an edge triggered or a level triggered interface. By edge triggered, we mean that the ePoll wait will return only when a new event is enqueued, whereas in the level triggered mode, ePoll wait will only return as long as a certain condition holds. For example, when a pipe registered to ePoll receives some data, a call to ePoll wait will return and the reader consumes some data from the buffer. In the level triggered mode, further calls to ePoll wait will return immediately, whereas for the edge triggered mode, ePoll wait only returns when new data is written to the pipe. Now, let's discuss the manner in which data is represented and carried over a networking medium. Since different machines or OSs use different word orderings, for example, they can use little endian ordering, which means that the lower bytes are in the first position, or the big endian ordering, where the higher bytes are in the first position, and these machines may communicate with each other over the network. So to ensure that the communication is uniform, the byte ordering used by the network is always big endian. So to essentially convert the data between the host and network byte ordering, we use a bunch of functions called H to N and N to H, and they're versions for both the long and short versions. Heterogeneous applications additionally need to exchange data, and this requires a common or unified data format. To achieve this, applications either encode the text to a specific format or use a serialization protocol like protobufs. And finally, different machines over the network are allocated unique addresses in either the IPv4 or the IPv6 format. IPv4 is an version widely used to identify devices on a network using an addressing system. It uses a 32-bit address scheme and stores more than 4 billion addresses. It is considered the primary internet protocol and carries about 94% of the internet traffic. IPv6 is the most recent version of the Internet Protocol. This new IP address version is being deployed to fulfill the need for more internet addresses. It was aimed to resolve the issues that are associated with IPv4, which we will not go into in this presentation. Next, we will discuss some tools that help us inspect the network traffic. We can use TCP dump to monitor the network traffic according to defined filters. These filters can be based on the source and destination IPs, the ports, the host name, the protocol, and many other things. In this example, the TCP dump monitors any 4 packets and then just exits. The next tool is known as Netcat, and Netcat is used for almost anything regarding TCP or UDP and Unix domain sockets. We can open TCP connections, we can send packets, listen on TCP and UDP ports to perform scanning of these ports, and amongst many other things. An example is shown in the image. We open a TCP connection on port 1234 in the left terminal. In the right terminal, we start a client. This establishes a bidirectional connection through which we can exchange data. For more complex protocols, we can also use the Wireshark tool, the details of which we will not go into this lecture. Sockets are powerful and conventionally used for networking applications. However, they execute syscalls, which are expensive in general. As a result, there are emerging technologies like DPDK and RDMA that improve performance by bypassing the host kernel. This figure shows an overview of how DPDK works. The NIC is bounded to a user space driver and is therefore no longer managed by the kernel. Additionally, the DPDK library maps the NIC's RX and TX queues to user space memory. The data is then moved from the user space memory to hardware, bypassing the entire kernel stack. And that's it for this lecture. We'll see you in the Q&A session.